An op-amp is a circuit component, just like a resistor or a capacitor. When you're building a circuit, you can decide which resistor to take depending on the value that you want in your circuit. Similarly, for op-amps, we define the value of the op-amp using different op-amp parameters, and the value of the parameters depends on the circuit that you're making. And when you're buying an op-amp from a shop or from a semiconductor company, the way you choose an op-amp is to tell them the specifications or the parameters that you want. So the first op-amp parameter that we will look at is CMRR, which is an abbreviation for common mode rejection ratio. Now, as the name suggests, there's something called a common mode which we want to be rejected, which means that the common mode should be eliminated. Now, what is this common mode? We've seen before that in an op-amp, we expect to get the difference of the two input voltages that we give it, right? We expect that Vout should be some gain A times V1 minus V2. This is the ideal scenario. But what generally happens is that another component gets added to it, and we see this component plus some other gain times V1 plus V2. This V1 plus V2 is called the common mode, while V1 minus V2 is called the differential mode. Ideally, we expect the differential mode gain to be infinity. Let's call this the differential mode gain. We expect this to be infinity, while this common mode gain, we expect it to be 0. So, how do you quantify what these gains for a particular op-amp are? The trend is to take the ratio of the differential mode gain to the common mode gain. Now, this value is generally to the order of 10 power 6, and that's very difficult to deal with, right? Like 10 power 6 basically looks like this. You've seen a similar problem before in terms of units, where if you have a unit, let's say if you have to write 1000 meters, we prefer to write it as 1 kilometer. In this case, the operation that you use to change from one unit to the other is multiplication. So there is another operation that we generally use for very large numbers, which is called the logarithm. So the log of 10 power 6 is just 6, and that makes handling very large values very easy. So how the CMRR is defined is you take the log of differential mode ratio of differential mode gain to common mode gain, and you multiply it by 20. So what we can infer from this particular formula is that as differential mode gain keeps increasing and as common mode gain keeps decreasing, your CMRR will keep increasing. So the ideal CMRR is equal to infinity. So higher the CMRR of your op-amp, it means the better the op-amp is. The next parameter that we'll be looking at is slew rate. To understand slew rate, let's think about a box. Let's say the box is on a floor. Rather than box, let's think of it as a car. It is on a floor. Let's say one point on the floor is marked V1, while another point on the floor is marked V2. If we expect the car to move from V1 to V2, we have to give it some time t to be able to move, right? Now, the faster the speed of the car, the lesser the time t will be. But I think it's pretty obvious to understand that the speed of the car is limited. You cannot expect the car to move from point V1 to point V2 immediately. Similarly, you cannot, when you're talking about the output of an op amp, you cannot expect the output to move from a voltage V1 to another voltage V2 immediately. So this rate at which the voltage changes, as you know, you can talk about a rate in terms of derivative d by dt, and so your slew rate is nothing but the rate of change of your output voltage with respect to time. This is the maximum rate at which your output can change. So what is the effect of a slew rate? Let's say my op amp has to deal with inputs which are moving very fast. Let's say this is grounded and I'm giving some input which is, let's say, a ramp. Now I expect this to be some value -0 into the gain, and so we expect the output to also look just like the input, but the rate at which the output can change, this slope, is limited. Let's say, to take a particular example, let's say our slew rate for some op amp is 1 volt per microsecond, and we give it an input which is changing, let's say, at 2 volts per microsecond. In that case, the output is not going to be able to follow the input, and your op amp won't actually behave the way you expect it to behave. So we have to make sure that the slew rate of our op amp, the op amp that we are going to choose, is higher than the rate of the maximum input rate that we expect. The next parameter that we are going to be looking at is the input bias current. So we spoke before about how we expect the input impedance of an op amp to be infinity. If input impedance is infinity, we expect that the current flowing in, because V by R is I, and if R is infinity, we expect current to be 0. So if input impedance is infinity, we expect the current flowing into the op amp to be 0. But the op amp has transistors in its beginning phase, and those transistors take current. And so there is some amount of current which is going to flow into the op amps. There are two parameters which are based on these currents. Let's say the current moving into this node is called I1, while the current moving into this node is called I2. The first parameter is called the input bias current. Bias might be a word familiar based on the bias current which you give to transistors to set their particular operating point. And so and bias current is something which is definitely necessary for a transistor, and so every op amp is going to have bias current if it's made up of BJTs. If it's made up of MOSFETs, it won't need bias current. But anyway, so bias current is defined as I1 plus I2 by 2. So it's basically the average of the two currents which are moving into the op amp. The other parameter which is based on this, the currents to the op amp, is called the input offset current. The word offset basically means difference, and so the way that is defined is I1 minus I2. What this means is, what is the like basically it's like the current in the going to the op amps is kind of tilted, and so one side is giving, say, a higher current than the other, and you want to try to measure how different the two currents are, and that is what the input offset current gives you an idea about, while the input bias current gives you an idea about how much current whatever is connected to your op amp, right, that source is going to have to pump in these two currents into the op amp. And so the input bias current gives you an idea about how much current whatever you're connecting before the op amp has to put into the op amp. The last parameter that we are going to talk about is like offset voltages. There are two kinds of offset voltages, input and output, and the two of them are basically related. Like what we just spoke about offset is that it's some kind of difference. So ideally, if I give, what we expect is to see V out is equal to A times V1 minus V2. So if we give V1 is equal to V2, we should get V out is equal to 0. But most of the times that does not happen. Even if the input voltages are equal, which means the differential input is 0, the output is non-zero. So that when the input differential voltages are like the differential voltage is 0, the voltage that we expect to see at the output corresponding to this 0 input, that voltage is called the output offset voltage. And now we know that this is not the expected behavior. What we want is if we give inputs to be 0, output should become 0. So what we do is that we give some input already to this before we give it our V1 and V2. So we try to give this particular voltage such that if V1 is equal to V2, V out should be equal to 0. And this voltage which you give to make V out equal to 0 when differential input is 0 is called the input offset voltage. It's quite easy to see a relation between these two voltages, as basically whatever is at input is getting multiplied by A and coming to the output. So we can see that the input offset voltage into the gain A of the op amp is equal to the output offset voltage. Now what values you choose for each of your parameters basically depends on the application that you have, the circuit that you're trying to build. And there are a lot of op amps available in the market for almost any kind of parameters that you might want.